So the question is now, how is it able to make 4 bonds but only 2 unpaired electrons? And the answer to that is what we call hybridization, right? That's the way that carbon is able to do what it does, right? So in order to do hybridization or mix orbitals or add orbitals together, what we're going to do is take the electrons in the outermost shell, which in this case is in this second energy level right here, right? We're going to add those orbitals together. All right. So we have a s orbital in that second energy level, the 2s orbital. And we have p orbitals. And I'm going to give this a color, right? So a hybrid orbital happens when you take those orbitals and you add them together, you get out a hybrid. And so I'm going to draw it like this so to exaggerate one of the lobes and make it make sense. Do you see how one of the lobes is larger than the other one?
Yes.
All right, so what that means is that when I add these two equations together, because orbitals are, remember we said that orbitals are the uh, graphs of the equations of the path of an electron, right? So it's a graph. The equation is graphed, and that when it's graphed, you get the path of the electron, whether it's in a P or S or a D or F or whatever. So orbitals are equations, right? So when you add these together, the part of the equation for the p orbital that has the same sign as the s, notice they're both shaded, is going to get larger, right? And then the other lobe is going to remain the same. So that's why the top lobe, this is what we call an sp hybrid. That's why the top lobe in the hybrid is a little bigger than the bottom lobe, because you add it together constructively, the s with the p and the part of the p that has the same sign as the s. Are we following that? We're okay with that?
I have a question.
Go ahead.
So the bottom
Mhm.
shape, does that represent the unhybridized orbital?
Or the unshaded, it's the unshaded part of the P. Because the S, when you add these two together, right, the S and the shaded part have the same sign. So they're just going to combine and make a bigger lobe,
Oh, okay.
right? So if the S is positive and the top part of the P is positive, when you add two positives together, it increases, right?
Right.
And so that's going to, that top part, that top lobe is going to increase in size.
Okay.
And the bottom lobe is not going to change, right? Because there's nothing added to it or subtracted from it.
Okay. Thank you.
Yeah, great question. All right, so that's a sp hybrid. Carbon exists in 3 different hybridization states. Let me write that here. Can somebody tell me what they are? If you watch the hybridization video. Right, 3 different hybridization states. And I'm gonna show you what each one is, what the numbers mean, all this stuff. So carbon can be sp3.
SP2 and SP.
Good, excellent. sp2 and sp. Those are the 3 hybridization states. What this literally means is that for if sp3, you've added together s plus px plus py plus pz, right? So you add the 4 atomic orbitals together. Let me move this down so I can write some notes. So for sp3, I added 4 atomic orbitals. That's going to give me 4 hybrids, right? So I added everything together, right? So the sp3 hybrid is going to look like, and I'm going to show you, so that the 3 is indicative of the fact that all 3 P's are involved in the formation of these hybrids. right? So I'm just going to get, sorry. Four hybrids. All right. And then what that means for carbon, if it's sp3 hybridized, that means that my carbon is tetrahedral. Actually, I'm going to put the orbitals in. All right, so you see the larger lobe and the smaller lobes are shown. It's tetrahedral. Has a 109.5 degree bond angle. And it has four, it can bond four groups. Right? Any questions about that? So if I take the S and all three P's and I add them all together, I'm going to get four sp3 hybrids.
So would you say it's like making like 4 copies?
Something like that. Something like that, yes. But the difference is like the hybrids have a slightly different shape because of the fact that when you add the S and the P together, that's only half of the P that's going to have the same sign as the S. So that's why the shapes are different. But yes. And that's if I took 4 atomic orbitals, I'm going to get 4 hybrids. Right? This is all esoteric right now. It'll make sense when we start looking at some examples. All right. So that's the sp3 hybridization state. And then the sp2, if we were just using logic, what do you think the sp2, what do you think the 2 means in sp2?
2 P's.
2 P's added to 1 S. Very good. Who said that?
Nadia.
Okay, thank you. All right, so let's go through the same exercise with the sp2. Right, what I'm adding together is S plus, let's just px plus py. What's left over? Because you know we have 3 P's, right?
PZ.
Z.
So PZ is just out here. And in this case, let me fix that because that looks like a 2. I don't want you thinking that's a 2 when you're looking back at the notes. Right, so that's PZ, and PZ is what we call unhybridized. PZ is unhybridized. How many hybrids am I going to get if I take 3 atomic orbitals and add them together?
3.
3 hybrids. Very good. Right, so 3 atomic orbitals is going to give me 3 hybrids. So I'm going to have 3 sp2 hybrids. I'm going to write the hybrids like this, plus like that. These are my hybrids. So this is sp2, 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 and then plus p. Right? That's plus 1 unhybridized p orbital. Are we following? We all right? So a carbon that's sp2 hybridized is going to look like this. So here's my carbon. I have a lobe, a hybrid lobe here. I have a hybrid lobe here. And I have a hybrid lobe here. So it's going to be like a triangle. It's trigonal. And then the unhybridized p orbital, I'm going to change the color for that. It's going to be here, above it and below it. Right, and I'll just shade one of those lobes. All right. So this actually is, let me give you kind of a 3D depiction. So it looks something like that, right? Whether this is the p orbital and the other hybrids, those are the other three groups around it, right? This is trigonal planar. It's a 120-degree bond angle. And it can bond three groups. Don't worry about the pi bond part because we're going to actually look at an example to explain that. All right, so it can bond three groups and it's going to form a pi bond to fulfill this octet. All right, I'm going to give you some examples and then all of this stuff will start clicking. So with the sp2 hybridized carbon, you got three hybrids, one unhybridized p, and trigonal geometry, 120-degree bond angle, and three groups around that carbon. All right, any questions so far about anything?
Yes, why is it an unhybridized P?
Because, okay, if you look at the hybridization state itself, the two means that only two of the three p orbitals are mixed with the s. So one of the p's gets left alone, left unhybridized. Because hybridization, remember, is adding the orbitals together.
Okay, thank you.
Mhm. All right, let's just logically push this to the next hybridization state, which is, how do I do that? All right, I don't know how I just did this, but that's okay. I'll just move this page down. Let's see. Okay, there we go. So now we're talking about the SP hybridization state. What do you think?
1P, 1S.
1p and 1s. Very good. So s plus p, and then how many unhybridized p orbitals?
2.
Two unhybridized p orbitals. Great. So you're going to have two atomic orbitals are going to give you two hybrids. All right, so you're going to have a hybrid here. Uh-oh. A hybrid here plus p plus p. Any questions about that?
Yes.
Go ahead.
I'm trying to understand the P.
Mm-hmm.
So how did you find like two? Like where did you get the two P's from?
Okay, let's go back to here. Right. Remember we said in the outer shell and the valence shell for carbon, there's four orbitals total, right? You got the 2s orbital, and then you got the three 2p orbitals, because p is the px, py, and pz, so there are three p orbitals. So that's a total of four. So if I added two of them together, two of them are going to be left unadded or unhybridized. Does that make sense or no?
Yeah.
Right. It's kind of like if you were going out and you had like three other friends, but you only took one friend with you, and y'all left, the other two are left untouched. Right. Or if you took all three of y'all went, three people left, one is left untouched. It's the same way here. So when you add these orbitals together, You can add them. You can add one S and one P. You can add the S with two P's, or you can add it with all three of them. And you're gonna the number that you add together is going to be the total number of hybrids that you get. So if you add together two atomic orbitals, so like take the 2s and the 2px, then you're going to get two hybrids, and then the other two orbitals remain untouched.
Okay,
Right. Did that clear it up
a little bit.
a little bit? All right. If it's not clicking, just say something. We're gonna figure out a way to get it to you. So with the SP, do you see that? So we took the S, one S and one of the three Ps. So that's two atomic orbitals. When we add those together, we're going to get two hybrids. And then the other two Ps, Py and Pz, they don't get hybridized. So they're still in their original state.
Are the tops big on purpose on the left side?
Yes. Remember I said when you take a S and you add it to a P, that one almost doesn't look. And you add it to a P, when these two add together, they're going to increase in size because the equations have the same sign. So that's why when I make the hybrid, one lobe is bigger than the other. Right? Did that answer it?
Yes.
All right. So with the SP hybridized carbon, that carbon looks like this. You have a hybrid here. You got a hybrid here. Right? And then one of your P's is going to be here, perpendicular. And then the other one is going to be, let me not use a different color. Here, like this. So it kind of looks like a propeller. Right? And then you have your hybrid coming through here. Right? So this SP hybrid or SP hybridized carbon has linear geometry. So it's 180, not Celsius, 180-degree bond angle. So you got 180-degree bond angle, and you have two groups and two pi bonds. All right, two groups, two pi bonds. So any atom that's SP hybridized is going to fit this criteria. It's going to be linear. It's going to have 180-degree bond angle, and it's going to make two pi bonds to fill out its octet. All right. So let's look at some examples and let's see if we can figure out the hybridization states of the atoms that are indicated. So let's
Excuse me, Dr. Russell.
Yes, go ahead.
Before you move on, I just had a quick question.
Go ahead.
Do the unhybridized p orbitals later translate into lone pairs, or is that a completely different thing?
No, the unhybridized p orbitals, that's a great question. The unhybridized p orbitals, they form your pi bonds.
Okay.
Yeah, so the pi bonds, let me say that right here too, because I was going to talk about it later, but when you make a pi bond, that comes from unhybridized p orbital overlap. Right, because what I don't want us to lose sight of is that when you add these together, right, if this is a SP and that's a SP and SP and SP, one of the consequences of hybridization is that everything gets one electron, right? Remember up here, let me go back to here. You see how we had 2 electrons in the S, and then 1 here and 1 here. So we got a total of 4 electrons. When you hybridize, the electrons get redistributed, right? So every hybrid is going to have 1 electron, just like sp3 here is going to have 1. This will have 1, 1, and 1. Because we started the discussion out saying how is carbon able to make 4 bonds, and this is how, right? Once it undergoes hybridization, the electrons get redistributed. So now every orbital has 1 electron in it. So I can put the electrons 1 here, 1 here, 1 here, and 1 here, and they can overlap with other orbitals to make sigma bonds, right? So this is an example of a hybridized orbital. So pi bonds come from unhybridized p orbitals, and then sigma bonds are the result of hybrid orbital overlap. Great question. And we're going to pull an example from the worksheet, and we're going to work through it and do a couple of things with it. We're going to discuss like the ramifications of whether something is SP, SP2, SP3, so on and so forth. Did that answer your question?
Yes, it did. Thank you.
All right. So what I'm going to do is, where's that question? Right here. Boom. I'm going to copy this example right here because this is what we're talking about. And then we'll come back to the other examples. And we'll be working through this like today and Friday. So let me add a page in here. I'm gonna just paste that. All right, so let's take that first example where it says it's CH3. And I'm going to write everything out because we're going to come back and deal with those skeletal forms and talk about condensed and skeletal and all that stuff. So CH3, CH2.
Would you recommend when we go through this sheet, writing it out on a separate sheet of paper?
You could, or you can write directly on it. But yeah,
Okay.
as we answer the questions, by all means, be following along so you can ask questions too.
Okay.
Yeah. Right. So that carbon has a negative charge up here. So I'm gonna put that in. What does that mean if an atom has a negative charge?
It has 1 more electron.
Electrons.
Yeah, it has extra electrons somewhere, right? So when you see carbon with a negative charge, that means it actually has a lone pair, right? And if you add the electrons up, remember, here's how we're going to combine all this stuff. So this is formal charge and hybridization in the same example, right? So it's valence minus actual, which in this case is valence is 4. Actual is what? Anybody?
5.
5. Good. So the formal charge is minus 1. I'm going to abbreviate that as formal charge. All right. Let's look at the carbon on the left. What is the hybridization state of that carbon? Right. Notice, first of all, it has all single bonds or sigma bonds, right? Right. And then how many groups does it have around it? Right. It's got a hydrogen here.
4.
1 here. Good. It's got 1 here and it's bonded to this carbon. So it has 4 groups. It has all sigma bonds. What's the hybridization state?
Is it SP3?
It's sp3. Right? The sp3 hybridized atom is going to have 4 groups around it. Period. Right? So that's a way to tell immediately. If you look at it and it has all single bonds and it's got 4 things attached to it, then it's going to be sp3. Now let's look at the other carbon. Right here, how many groups are around that?
4.
Did I hear somebody say 4?
Yeah, is it 4?
It's 4. We got hydrogen, hydrogen, carbon, and then the lone pair. I know it looks weird just sitting on top of the atom, but the lone pair is actually sitting in an orbital, right? So that's a group as well. So the lone pair also counts as a group. So in this case, the lone pair is a group. So this carbon also has 4 groups around it. What's the hybridization state?
SP3.
It's sp3. Any atom with 4 groups around it, even if one of the groups is a lone pair, it's sp3. So that lone pair, let me put the charge back, is sitting in an orbital. That orbital has a shape, and so it's a group just like the sigma bond to hydrogen or the other sigma bond to carbon, like we see here. Any questions about that? All right, let's do C. We have an oxygen, and we have 3 groups attached to it. You got a lone pair and a positive charge. The lone pair is not shown, but it's understood because oxygen has to fulfill its octet. As a rule of thumb, if oxygen has 3 groups attached, it's only going to have 1 lone pair. If it has 2 groups attached, it'll have 2 lone pairs. If it has 1 group attached, it'll have 3 lone pairs. So that's general. So oxygen with 2 groups is going to have 2 lone pairs, and then if it only has 1 group, it's going to have 3 lone pairs and a negative charge. Right, let's figure out the formal charge. How do we know that that's +1? Or why is it +1? What's our method for figuring formal charge out?
Valence electrons minus formal charge.
Valence minus actual, is that right? What's the
Yeah.
valence for oxygen? Based on the periodic table. If
6.
6, it's in group 6, right? Boron is group 3, carbon is group 4, nitrogen is group 5, oxygen is group 6, and then the halogens are group 7. So it's group 6. 6 minus what? You got a lone
5.
pair. Great. Lone pair and 1 electron from each bond. So 6 minus 5. Formal charge is +1. Now, what is the hybridization state of that oxygen? How many groups? Is the lone pair a group?
Yes,
Yeah.
so it'd be
It is, right?
SP3.
Yeah, it's sp3. Right, the lone pair again is in an orbital. And so it's a group. It has a shape, it has a direction, just like the sigma bonds are pointed out away from it. That geometry, it has a shape and a direction, so it'll contribute to the geometry. What's the geometry if it's sp3?
Tetrahedral.
It's tetrahedral. Good. All right, we're gonna do E and E, D, and G. We're gonna do those. E, G, D. Let's do E. Look at the carbon that the arrow is pointing to. So let's write that out. We have a carbon, not like that. Carbon with a triple bond to another carbon. And this is H and H, and it's asking for the hybridization state of this carbon. You can do this 1 or 2 ways. You can count the number of pi bonds to carbon, or you can count the number of groups. And I'm gonna explain both. how many groups are attached to this carbon? Not bonds, groups, because carbon is always going to have 4 bonds unless it's charged. If it's positive or negative, that means it's going to have 3 bonds and either a plus charge or if it's negative, it'll have a lone pair and 3 bonds. But if it's neutral, it's always going to have 4 bonds and it'll never have more than 4 bonds. So how many groups are attached to that carbon? Right? By groups, I mean what's on the left of it and what's on
Is
the
there-
right of it.
There 4.
2.
2. There are 2 groups. Y'all following? I heard somebody say 4. Let's clear that up.
Is that so? I think I was just saying 4 because I saw the 3 bonds and I was thinking, okay, well, 3 bonds and then there's another bond on the other side. You're not counting necessarily those, you're just counting what it's attached to.
Yeah, we're not counting the bonds because it's always going to have 4 bonds,
Okay.
right? But we count the groups, and that helps us to determine quickly what the hybridization state is. So if it's got 2 groups attached to it, then it's going to be what? Anybody?
Linear.
It's linear, good, which corresponds to which hybridization state?
SP.
SP, very good. So it's linear and it's SP. Let me show you how this works, right? Because remember we said SP, you have a hybrid here and you have a hybrid here, right? And then you have 2 unhybridized p orbitals like so, right? And that for this triple bond, let me show you how that works. So you have another carbon on the other side that has, let me fix that up. Same hybridization state. And then it also has a unhybridized P here and 1 here. Right, so they're perpendicular to one another. And each one of these has an electron in the orbital. So I'm gonna put electrons here, here, 1 here, and 1 here. Same way here, 1, 2, 3, 4. So when these 2 come together right here, those are hybrids. So when those 2 hybrids come together and share a pair of electrons, what kind of bond is that again? Did we talked about that on Wednesday, right? Or Monday?
Covalent.
It's a covalent bond. Very good. So when those 2 overlap, I'm going to get a covalent bond between those 2 carbons here and here, right? I have another P that's back, another hybrid that's back here that's going to bond to that hydrogen. But this right here is going to be a covalent bond, right? And then that carbon still has this P out here. And then it still has this P out here. I'm gonna put the electron on this side instead of the other side to make it make more sense. Okay. That's better. All right. And then it also has the p orbitals going in the vertical direction with electrons. So now this, when the 2 hybrids come together, the green bond, covalent bond, I'm showing as the addition of those 2 hybrids, that's a sigma bond. Right? So that triple bond is going to have 1 sigma bond. And then the fact that these 2 carbons come together, the p orbitals here and here are close enough to overlap. Right? And so that's both of those are going to give you what we call a pi bond. right? So that triple bond in that sp hybridized carbon is made up of 1 sigma bond and 2 pi bonds. But it's the sigma where that's how your groups are going to be attached, right? Because on the back side, I'm going to add hydrogen. Right, and that's also hydrogen is 1s, so that's going to overlap with that hybrid and give you that sigma bond to hydrogen. Right, so that carbon has 2 sigma bonds and 2 pi bonds for a total of how many bonds?
So does it have 2 pi bonds and 1 sigma bond?
Well, yeah. So the triple bond is made up of 2 pi bonds and a sigma bond. But the carbon itself has formed 2 sigma bonds, right? Because this is also, let me point it out. This is also a sigma bond right here, right? That's sigma to hydrogen. Is that right? And then if we look here, we can say that I always just pick the middle bond and a triple bond. So the middle bond is sigma, and then the other 2 bonds are pi bonds. So the carbon itself can make 2 sigma bonds and 2 pi bonds if it's sp hybridized, because it's got to have 4 bonds to it. Yes, no, it's very quiet. So that carbon that's in that triple bond is sp hybridized. And the way we know it is because we can look at the number of groups. It has a hydrogen on one side, has a carbon on the other side, right? And it's linear, right? And that also tells us that it's sp hybridized.
I have a question.
Go ahead.
Okay, can you re-explain how it's 2 pi bonds?
Sure. So let me put this here. This is hybrid overlap.
Wait, oh, sorry.
Go ahead.
Oh, I was saying, is it 2 pi bonds because there's a overlap with
Yeah.
the
So you have two
unhybrid-
unhybridized p
Right.
orbitals that are overlapping. You got the blue ones overlapping to make 1 pi bond, and the red ones overlapping to make another one.
Oh, so it's like, because when I looked at it, I thought, okay, there's 4 because you have the 2 blue ones on top, then the 2 blue ones on the bottom.
But remember they're connected, right? That's a p orbital. So it's just 2 lobes of
okay.
the same orbital.
Oh, okay.
Yeah, it looks kind of crappy. Matter of fact, let me fix this one over here because that does look disconnected. But it's 2 lobes of the same orbital. So that's like that. And on the other side, it's the same way.
Is it the py and the pz that we are talking about as well on
Yes,
IDA?
yes. Because the px was used to make the hybrid. That's a great question. So the sigma bond comes from hybrid overlap, and the pi bond comes from what? Anybody?
unhybridized
Unhybridized
overlaps.
p orbital overlap. All right. We got time to do one more of these. We're gonna hit this Friday too, so make sure you have it somewhere. Let's actually do G real quick. So I'm going to draw this out because they have it written in condensed form, and we're going to talk about that on Friday too. Condensed versus skeletal versus Lewis, and all. I'm gonna write it out in Lewis form. So this is CH. CH3, this is CH. I'm gonna write it out like that. So it's asking for the hybridization state of the N carbon, the terminal carbon right here. And it's asking for the hybridization state of this one. Okay, so look, let's start on the end. What do you think? How many groups are attached to that carbon?
3.
Oh man, this is gonna be a good semester. 3 groups. You're exactly right. Right? You have a group here. Let me pick a different color. You have a group here, and a group here. Yes. So we're
Yeah.
looking at the carbon that's
Yeah.
highlighted in yellow. So what do we know about a carbon if it has 3 groups attached to it? We know that it can only be one of the 3 hybridization states. Right? Speak up a little.
SP2.
It's sp2. Very good. Right? And notice the carbon has a double bond, right, to that other carbon. That double bond is made up of 1 sigma and 1 pi, right? Double bond, let me write that in. So that double bond equals, that's 1 sigma bond and 1 pi bond. But if you notice, carbon is maintaining its octet. It's got 4 bonds to it, so it's got 8 electrons around it at all times, right? So that carbon is sp2. And that double bond, just like down here we did the triple bond, the sigma bond is going to come from what? What type of overlap?
The
Hydroxide.
Yeah, hybrid orbital overlap. And then the pi bond is going to come from what?
The unhybridized.
Unhybridized p overlap. All right, I'll draw that out Friday because I want to run out of time. But look at the middle carbon. What do you think? sp3, sp2, sp, and if you, whatever your answer is, explain it to me.
I think it'll be SP.
SP, you're exactly right. Who was that?
So now,
Yeah, you're absolutely right. Why do you say it's SP?
because it has 2 groups.
2 groups. Very
carbons.
good. It's got a carbon on this side and it's got a carbon on that side. So it's got 2 groups attached to it. Notice also it has the same makeup as a triple bond. It's got 2 sigma bonds to it and what? And 2 pi bonds. Are you following? Because each one of the double bonds is made up of a sigma and a pi. Or yes or no?
Yes.
So if you got 2 double bonds on that carbon, it's just like the triple bond down here, right? Did it not have 2 sigmas and 2 pi's? And it was sp hybridized?
So there are 2 sigma bonds and 2 pi bonds for the carbon in the middle.
Yeah, because the double bond itself, 1 double bond is made up of 1 sigma and 1 pi.
Right. Okay.
And if it's got 2 double bonds to it, which is still a total of 4 bonds, 2 of those are going to be sigma bonds, 2 are going to be pi bonds. Because remember, if it's sp, how many unhybridized p orbitals is it going to have?
2.
2.
And those unhybridized p orbitals are where your pi bonds come from.
Okay. Thank you.
Everybody good? I know this is kind of a lot, but I like doing it this way, where we just jump in and work the examples based on what we have. We start applying this stuff. If there are any questions, ask them. Because we're going to stop here.
I have a question.
Go ahead.
So so you just said that the 2 pi bonds come from the unhybridized p overlap. So that's the py and pz orbitals, right?
Yes. If it's the sp, if it's sp hybridized, yes.
Okay.
Great question.
So the triple bond is 1 sigma and 2 pi's. Okay.
right? So you can have a single bond, a double bond, which is 1 sigma and 1 pi, or a triple bond, which is 1 sigma and 2 pi. All right, any questions, anything? So we're gonna work through several of these other examples. We're not gonna do every single example, but we're gonna work through several of them. And whatever we don't do is when you turn it in, if it's a problem we didn't do, that's fine, unless I tell you to do it at home or do it on your own.
So at the end, we'll turn in these problems.
Yep. When we get to the day after the exam, you just go in Blackboard, find the link and upload it.
If we're writing it electronically, can we do it that way as well?
Yeah, absolutely. Because that way you can write directly onto the document. Yeah. Either way, you want to write it, edit it electronically, if you want to print it and write it, or if you want to write it out in your notebook, either way is fine.
When we turn it in, are you gonna want us to show all the work of how we got it? Like I have the work on a separate sheet of paper, but then I'm writing like the answer.
Yeah, you can submit all of that.
Okay,
Yeah, just use Cam scanner
okay,
and turn it into a PDF and you can submit everything.
okay, perfect.